Welcome to the extra class for the course Mechanics of Fiber Reinforced Polymer Composite Structure. Today I am going to just brush up some concepts which will be covering all the assignments and the questions that we have discussed. First concept is what is composite. So composite materials have two or more different constituents that is carbon that you can see in the example. It has for example, carbon fiber and epoxy pipes where they have carbon fiber and epoxy. Concrete is a mixture of adhesive aggregate giving a rubber strong material that is very widely used, or hybrid composites. Now in a composite material, the matrix phase is continuous but less stiff and weaker, while the reinforcement phase is discontinuous but more stiff and strong, as you can see in the diagram. The constituents in a composite combine in macroscopic scale, whereas those in alloy combine in a microscopic scale. Two or more materials combine. When in macroscopic it becomes composite, and in microscopic it becomes alloy. Reinforcements generally act as load-bearing members, whereas the matrix acts as binder. So, uh, when we are correlating the stresses and strain, then for an isotropic material, it has 9 stress-strain components. And in the generalized Hooke's law, it shows that sigma ij is equal toCijkl epsilon kl, where ijkl is equal to 1 to 3.Cijkl is a fourth order tensor. The type of materials and the number of independent elastic constants. So types of materials that we have studied are anisotropic. One is the property of a material which allows it to change or assume different properties in different directions. Monoclinic, which is elastic solid, has one plane of material property symmetry. Orthotropic, all three planes of material property symmetry. Isotropic, transversely isotropic, have three orthogonal planes of material property symmetry, and one of them is a plane of material property isotropic. And isotropic, where properties remain the same in different directions. Isotropic materials have only two independent elastic constants, that is the Young's modulus E and the Poisson ratio mu. The shear modulus G can be calculated as G equal to E by 2 1 plus mu. So according to these definitions and the independent elastic constants available, we know that initially there are 81. After shear symmetry, it becomes 36. After that, when we consider symmetric, that becomes 21, which is for an isotropic material. Then for monoclinic material, it becomes 13. For orthotropic, it is 9. Transversely isotropic, it is 5. And for isotropic, it is 2, which is the bulk modulus and the Poisson ratio. Young's modulus and Poisson ratio. Now, this diagram, this relation matrix can be asked where for different materials, which of the components has zero and which are non-zero. So from the diagram, from this matrix, you can see which terms are known as the extension coupling, shear and shear coupling. So for a fully anisotropic material, all the shear and shear extension coupling terms are non-zero. For orthotropic material, all the shear extension coupling terms are zero. Isotropic material, all the shear and shear extension coupling terms are zero. Monoclinic material, some of the shear extension coupling terms are zero. And for transversely isotropic material, all the shear and shear extension coupling terms are zero. So, according to which material they have asked, you have to remember which all terms will be zero for this stress strain matrix or the compliance matrix and stiffness matrix. So, a unidirectional lamina is heterogeneous and anisotropic. Heterogeneous means that the properties are location dependent, and anisotropic means the properties are direction dependent. Now, there are two types of orthotropic lamina, specially and generally orthotropic lamina. So, whenever the analysis axis, that is XYZ, that is we also call global axis, if it coincides with the material axis, that means the direction in which the fibers are aligned is the same as that of the XYZ axis, then we will call it specially orthotropic. And when it is not aligning with the general global axis, that means if there is some angle, then it is generally orthotropic lamina. So specially orthotropic lamina are those which has 0-90 kind of fiber alignment, and generally orthotropic lamina are those with some angle. Now the stress strain matrix of an orthotropic material when defined by using engineering constant can be measured by using an UTM. So here you can see the stress strain matrix. So it has this coefficient. These are the for the compliance matrix. All these coefficient values can be found by using the engineering constants which which are available to us by uh, testing them in an UTM. So first, when we have a compliance matrix, as you can see here, this is a compliance matrix. After that, we have to reduce it. This is the reduced compliance or stiffness matrix that you get by considering the assumption that the thickness is very less. So the properties in direction 2 and 3 are almost same. According to that, we have reduced the previous stiffness and compliance matrix to this reduced form. Now this is uh, now this have to be transformed into a transform reduced stiffness matrix where there some angle is present. So according to the angle in which the fibers are aligned, we will use the transformation matrix, and we will multiply the transformation matrix in such a way that we will get a transformed reduced stiffness matrix. So this is the transform reduced compliance matrix. Similarly, there is stiffness matrix also. Now, failure theories. So, there are two types of failure theories, non-interactive theories and interactive theories. Non-interactive theories, in which comes the maximum stress theory and maximum strain theory, whereas interactive theories come Psi-Hill theory, Hoffman failure criteria, and Psi-Wu theory. Okay, so non-interactive means when we are only studying a single parameter, and each of these parameters are uh, not considering with each other. That's when non-interactive theories come. And interactive theories are when one parameter the whole failure depends on more than one parameter, such as it depends on stress also, strain also, shear also. At that time comes the interactive theories. So mostly the questions are asked for maximum stress theories and Psi-Hill theories. So these are the formulas given for maximum stress theory and Psi-Hill theory. Now comes the properties of the properties of a whole lamina. So each lamina constitutes two materials, that is the reinforcement and the matrix. So the reinforcement we consider it as the fiber, and the matrix we give the name matrix and we put the symbol M. Now for longitudinal Young's modulus and Poisson ratio, you will see it goes with the mixing rule. That is, the overall modulus of the lamina is equal to the modulus of the fiber multiplied by the volume fraction of the fiber plus the modulus of the matrix and volume fraction of the matrix. So that forms for the longitudinal Young's modulus, and similarly Poisson ratio. Whereas for transverse Young's modulus and shear modulus, The mixing rule is such that 1 upon the modulus of the whole lamina is equal to the fiber volume fraction divided by the modulus of the fiber plus matrix volume fraction divided by the modulus of the matrix. Now, it has been seen that the when we calculate the transverse Young's modulus and the shear modulus by this equation, then the values are very much different from the experimental value. That's why comes the Helfenstein method. So you can see these are the equation for the Helfenstein method. So one thing you have to always remember when you are doing Helfenstein method, for transverse modulus evaluation, zeta will be equal to 2, and for in-plane shear modulus evaluation, the zeta value will be equal to 1. Now comes the minimum and critical fiber volume fraction. So once the fibers have broken, the stress that the matrix can take alone is given as the matrix stress, ultimate matrix stress multiplied by the the matrix volume fraction. Only if the stress is greater than the ultimate tensile strength is it possible for the composite to take more load. So the volume fraction of fibers for which this is possible is called the minimum fiber volume fraction. So fiber volume fraction, minimum fiber volume fraction is the amount of fiber volume fraction such that the ultimate strength is lesser than the strength of the material even after all the fibers are broken, and we are reaching the ultimate strength of the matrix. At that time, we will get the minimum fiber volume fraction. Whereas, it is also possible that by adding fibers to the matrix, the composite will have lower ultimate tensile strength than the matrix. In that case, the fiber volume fraction for which this is possible called the critical fiber volume fraction, and the equations are given to find out the values of fiber volume fraction which is minimum and critical. And the effect of moisture and temperature on a lamina. So, the effect of moisture and temperature only falls on the strain. So, strain values change whenever there is the effect of temperature and moisture. So, you can see the strain due to temperature change is equal to the change in temperature value multiplied by the coefficient of thermal expansion. Whereas, when the change in the strain due to moisture is equal to the moisture concentration and the coefficient of moisture expansion. Now, in orthotropic lamina, the direction dependent properties could be controlled or tailor made by changing types of fiber matrix, and for a given fiber matrix combination by changing fiber orientation and fiber volume fraction. So, in the assignments, there were questions directly to this statement. Still, people are having confusion. So, just remember the statement. Then comes the ABBD matrix. So ABBD matrix is useful when we are first we consider talked about only the lamina, then comes the whole laminate. So when we are talking about a whole laminate with different stacking of different angles, at that time the ABBD matrix is required for us to find out what will be the overall stress and strain in the whole laminate. So for that, the equation to find the ABD matrix is given here. So in assignments, I have solved it a lot of time and also have tried to make you understand how to find the A matrix. So A matrix is first you will need the stiffness matrix, and from stiffness, reduced stiffness matrix for each lamina. You have to multiply it with the location of that lamina and then do the summation. That will give you the A matrix. Similarly, the equation of B matrix and D matrix will include the location of the lamina and the reduced stiffness matrix of the lamina. The global strain values is equal to the mid-plane strain plus the location of the lamina into the curvature. Most of the questions which we have dealt with, they are most simpler as this take the curvature equal to 0, and mostly the global strain is equal to mid-plane strain. But if they ask in the question about this, if there is a curvature also, then you have to take this equation. Now, in-plane and out-of-plane stresses in a laminate. So out of plane stresses at the free edges is found when the stress, the shear stress in xy direction is not equal to 0. At that time, the out of plane strain that we get is shear in xz direction. Whereas if we have the stress in y direction non-zero, at that time the out of plane stress we will get is tau yz and sigma z. And these out of plane stresses are the one which are responsible for the delamination. And the last section was about the transverse deflection and buckling load. Transverse deflection, buckling load, and the natural frequency of transverse vibration. So as we discussed, this is the overall equation of the transverse deflection. But when we are talking about specially orthotropic symmetric lamina, as I said, specially orthotropic is those which has 090. So for 090, as it is symmetric, the B matrix will be equal to 0. And for 090, the load and shear combination is also equal to 0. That's where the A16, A26, D16 and D26 values will be equal to 0. So for this case, the equation for the transverse deflection will decrease into this equation. And in this equation, you see only the coefficients of the D matrix are required. So, if you know what will be the conditions of the D matrix, then you will be able to find the value of the transverse deflection. Similarly, in buckling load, this is the final equation. And by putting the conditions of specially orthotropic and symmetric laminate, the final equation get condensed to this one. And finally, the natural frequency of transverse vibration. So this is the direct equation from the literature that is used to find the natural frequencies of transverse vibration. So these are all the equations and the concept that we have studied and have done assignments on them. So it was just a revision. So any doubts in these one?
Ma'am, I'm audible.
Hi, yes, you are audible.
First of all, thank you so much for being with us and solving our assignments from the month of February. It's really nice efforts by you.
Thank you.
Okay. And ma'am, my query regarding exam is, can you brief us how they are going to set the final exam paper? Like
Uh,
how many theory questions are there, or how many examples, or like that?
a final exam is all dependent on sir. I have no hand in the final exam question paper or anything. So I think others, if they have given an exam on NPTEL, they can help you with discussion like last time of what type of questions come. But the question paper for this subject only sir knows, and he is the one who creates the question paper. I can't help you with the final question answer.
Okay, okay. So whenever you are going to meet to sir, then just ask them. Means it's difficult to use scientific calci, which is online given by the NPTEL, and the equations are too much. And in our graduation, we are also provide the design data book for such kind of designing. So equations are too much bulky, and it's next to impossible. Means we have a lot of efforts to remember that, uh, but it's quite difficult, ma'am.
I think the bigger, like the difficult equation, which I will say the final assignments which we did,
Yeah,
like
yeah.
for transfers and all,
It's
it will
completely covered
be
by this PPT.
the questions will be mostly on the concepts. I don't think they will directly ask you to solve any big questions, but if you know the concepts, then small like the assignment questions on MCQ, those type of questions you will be able to solve. That the whole calculation will be for easier questions only because there is a time limit. So accordingly, they will prepare the question.
Yeah, yeah, definitely, definitely. Because we have to find out somewhere A inverse, and the inverse matrix. It's too much lengthy, and also like transform, reduce, complies matrix, and all that formulas are
Yeah,
too much lengthy, ma'am. See, in assignments and your guidance, we can easily go through search node or your PPT. We can solve and achieve handsome marks in our assignments. But we are much conscious about this exam, so it's uh, hope so. They are going to provide some equations and all the data.
I think some major equations they might give in the question paper. I think it's better there is a discussion portal also for this subject. So that will
Yeah,
directly go to sir. Then maybe you can ask these
yeah,
questions
yeah.
there.
Yeah, but I think the sir was too much busy. So I put lots of mails but sir is not going to be answer. Maybe busy schedules. So let's hope for the best for the exam.
Okay. I don't know
Um,
how to contact sir because actually sir is from other institute and I am from other institute. That's
Okay,
why.
okay, okay. And one more help, ma'am. My PhD topic is regarding this. May I contact in your future for such academic help?
Yeah, yeah, you can contact me. Give me your email ID in the messages. I will mail you. Then you can have my
Fine, fine.
contact through mail.
Okay, okay. And thanks a lot, ma'am, for your support and enthusiasm.
Thank you. Can you give your email ID in the messages? I
Yeah,
will mail you.
definitely. Okay. I just drop it, ma'am.
Okay, I will mail you to this email ID.
Fine, fine. Ma'am. Okay. Have a nice evening.
Thank you. And all the best for the exam.
Thank you. Thank you so much, ma'am.
Okay. Does anyone else have any doubt?
Yes, ma'am, I have.
Yes, Alam. Tell me your doubts.
Ma'am, week 4, question number 3, problem solving. Hello?
Yes, yes. Wait, I will open the from the sample questions.
Yes, ma'am.
Which one? At week 3 or 4?
Ma'am, week 4, question number 3.
This one?
Did you give?
Is this the question?
Yes, ma'am.
Yeah. So what is the doubt in this one?
Ma'am, this, how this sigma 1 series, sigma 2 and tau 1 2 is calculated?
Can you repeat your question? Kalpan, I have mailed you. Okay.
Okay, fine. Thank you.
Yes. What is your question? How to find what?
Now, how to find this, I mean, tau sigma 1, sigma 2 and tau 1 2? This, when I calculate this, then this number is, I found is different.
You didn't get these values.
Yes.
Okay. I will resolve it and check them.
And please share this video on YouTube.
Yeah, I will be sharing this by tonight. I will share.
Okay, okay, fine. I left the meeting. Okay.
Huh?
From your side, it is end up now, ma'am.
Yeah, yeah, from my side it's end. If you have doubts, you can stay.
Okay,
Otherwise, you can leave.
okay, okay. Thank you.
Ma'am,
Hmm?
can you give me your email ID? So if any doubt, I mean, in this wiki within the day, week, then I will send you.
Okay, I will
I will
mail you
contact.
guys. Yeah. Wait, first I will solve this and then I will mail you. Which value you were not getting correct?
Yes,
Which one you were not getting the correct value?
this one, ma'am. Tau 1, 2, like that.
Tau. No, I'm getting the same value. I did the whole
Okay, ma'am. So
calculation. Check your calculation
maybe
once. Yeah, the same values came. You do the calculation again. Uh,
okay, ma'am.
Take the cos and sines properly.
Okay, ma'am.
Any other doubts?
Yes, ma'am. I have another one. I will. This one, ma'am. A dry bundle of fiber subjected to tensile load may fail to a stress that lower than the ultimate tensile stress for the fiber matrix system. Okay, ma'am.
Hmm.
Second option is the ultimate strength of matrix more than that of the fiber. This second, the ultimate strength of matrix is more than that of fiber. This one is the wrong. Okay, ma'am.
Yeah.
But for the dry bundle of fiber subjected to tensile load may fail at a stage that lower than the ultimate strength. This also, ma'am, I think this falls.
No, the fiber strength is the highest, then comes the composite, then comes the matrix. Okay. So fibers,
No, ma'am. These fiber subjected to tensile load, okay, ma'am,
yeah,
may fail at a state lower than that ultimate strength is a fiber matrix.
that's what I'm
This
saying. See, the ultimate strength of the fiber matrix is the highest, is not the highest, it's the middle. So highest will be of dry bundle. So if the dry bundle is failing before the ultimate strength of fiber matrix, that will be incorrect one. Did you understand? Highest will be your fiber bundle strength. Highest
when
strength is
it's
fiber.
I mean then fiber matrix when composite after the composite it will its ultimate strength is lower. I mean
From the highest is fiber, then composite. Composite ultimate strength is lower than fiber, and then the
oh,
lowest is matrix.
okay. Ma'am, next question is week 8 question number 6 7.
Which it's this one.
Yes, ma'am.
What point is the doubt?
Ma'am, I did not understand this how this will make. I mean, this will calculate.
Um, So, in the previous one, question number 6, you can understand till how to get the global mid surface trains, right?
Right, ma'am.
Okay, so you got the global one. So after getting, um, okay, so previously you got the global strains. Okay, so now here there is no curvature. Global strain will be equal to the mid plane strain. So that is separate. So that was because of the load, direct load you took. You from a load you get a strain. So that was a separate one that you got epsilon x, epsilon y, and gamma xy. Keep it aside. Next is in this question they are only considering the strain due to the temperature change. So To find the strain because of temperature change is all that is done in this question. So first will be transforming the thermal coefficients from a global strain to the principal axis, that is alpha x to alpha 1, supposed to like that. Then find the free thermal
Okay, ma'am.
strain from, hello?
Yes, ma'am.
Then
Yes, ma'am.
find the free thermal strain of each plant. So that will be equal to the temperature change into the the coefficient alpha x, alpha y, alpha xy. Now you got the thermal strain of each ply. From that, there is this equation to find the that of the whole laminate. So this equation where the load for thermal is equal to del T summation of all the reduced stiffness matrix multiplied by the thermal expansion. So this is a separate equation only for thermal expansion. So from that you will get the strains because of thermal expansion, and then the residual strain is what they have asked in this question. So residual strain is, suppose there is some strain happening because of some mechanical change, and plus there is some because of the thermal. So the residual is the difference between these two. That is what they have asked. So first, whenever thermal strain they will ask in the question, first you have to find the mechanical strain. Then by this equation you have to find the thermal strain, and from the difference of those two you will get the residual strain. Okay, so that's what they have asked in the question, to find the residual thermal strain.
Okay, ma'am. Ma'am, can you give me your contact number so that's any problem? I mean, within this week before the exam, so I contact you.
I'm sending you my email ID. You can mail on my email.
Okay, this is Afzal Make Get Mechanical. This is the my email ID, ma'am.
Yes, yes, I'm sending you.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Okay, thank you. All the best for exam.
Okay. Thank you, ma'am. Thank you. Okay.